I'm going to talk about closing preferences based on body shape. This is the first time that we study closing based on body shape. In this, to study closing preferences based on body shape, it's a very challenging task. Online shoppers tend to send back the bot closing items 63% of the time, which 52% is due to the fact that it doesn't fit, but the fitness of the closing is not about the size, but it's also about what type of closing category and the style fits your body shape, the best. We want to better understand what which clothing goes well with your body shape. Online fashion data is a very good source for this, but it's very challenging, so we propose a 3D body shape to study this correlation. There are previous work which done a great job on 3D body shape estimation. However, they're not very well in predicting a diverse shape. So to solve this problem, we introduced a multi-photo shape estimation, which we collect which we use multiple photo of the person along with their 2D joint and body silhouette, and we estimate their 3D shape, and we show that we can have higher variation in body shape of the person. To study the relation between the body shape and clothing category, we collected a new data set which calls fashion takes shape. So we have people with different variation in body shape from average to plus size people. We collected manually, so we are sure that we have different types of body shape. We collect multiple photos of the person. They have lots of photos. We collect multiple photos of them, and we extract their target category and we estimate their body shape. So we have the clothing target category information and their body shape, estimated body shape. So here you can see the period on the clothing category and the body shape. As the blue bars are for average and thinner person, and the red bars are for plus size users. And with 87% of accuracy, we can separate plus from average body shape, which shows the informativeness of our shape estimation. So here you can see, yeah. So the positive number are average body, and then the more it goes to negative, they are plus size body type. The red curve shows, for example, for people wearing cardigan, and the blue curve shows people not wearing the cardigan. Then we build up a statistical model using our period to predict the clothing preferences for different body shapes. So if you have a beta of, for example, -1, we can tell how likely is for you to wear cardigan or like compared to a skirt or any other category. And so for further results we did it for 15 different categories. We compare our shape estimation with several baselines, and also we show negative log likelihood of our method or a statistical method also on several baselines on our paper. So for further information, please read my paper and come to my poster. Thank you.
Any questions?
Yeah.
Are the clothing types manually labeled?
What?
The clothing types you have, are they manually labeled?
So we didn't manually label. In this tutorial, you have tags that people actually manually label their own clothing there, so that I extract all the tags. There are also attributes, but we didn't work with attributes, and there are also user likes, votes, and other user opinion. That they're all available in this dataset. We didn't use it, but they're available. Yeah.
But then your 3D border are really like annotated. So you do have the 3D border between from the images to the 3D border.
Yeah. So our model is a statistical model. It's not, you don't need any training, and you just need 2D body joints, and you get 3D body shape of the person. Yeah. It's also available. It will be available. The code and dataset will be available.
Alright, okay, our next speaker, and the last for this oral session, is by Fadime Sener. She's a student at the University of Bonn, and she's presenting us about unsupervised learning and segmentation of complex activities from video.
Hello everyone, I am Fadime, and today I'm going to present the work I did with my supervisor, Angela Yao.
And our title is Unsupervised Learning and Segmentation of Complex Activities from Video. So we define a complex activity as a procedural task with certain steps and sub-activities that follow a loose ordering. Here, in this case, for making coffee, we have these 6 sub-activities. Our aim is to discover and segment the steps of a complex activity from collections of video. We assume we are given a collection of videos, all of the same complex activity, and we define K, the total number of sub-activities. And our goal is to find and temporarily localize each of these sub-activities. What makes this task so difficult? First of all, in these complex activities, the ordering is loose but not fixed. There might be a lot of background or garbage frames which are not relevant to what we are interested in. And there are huge appearance variations. For example, here you see some examples of the filling water sub-activity. And the appearance variations can also be quite confusing. For example, here you see 2 different sub-activities, put stow and remove stow, that have very fine grain differences. And sometimes, in these complex activities, you skip some steps. So the way we do unsupervised discovery and segmentation is to iteratively learn, given some initial segmentation. We then alternate between learning a distributive appearance model and learning a temporal model of the activity. Then we construct a new segmentation, and we repeat. We use a redundant form of representation where we split the actual segmentation representation into a bag of sub-activity labels and the ordering. If we put everything together, this is the plate model of our overall model. Given some segmentation Z, we can define some appearance model. The segmentation is composed of the bag of sub-activity labels A, which we model as a multinomial, as well as the ordering pi, which is based on the Mellows model. So the more novel aspect of our model is how we handle the temporal ordering. We treat the ordering as a sequence of permutable sub-activities. In this way, we can define a probabilistic distribution over permutations. In particular, we use a Mellows model, and the Mellows model is defined as follows. We assume a canonical ordering sigma, and given an observed ordering pi, we can then define the likelihood of this ordering as an exponential function based on the distance between the canonical and the observed ordering, and draw some dispersion parameter which controls how much distance influences the likelihood. So the advantage of using a Mellows model is that it allows for enforcing global ordering constraints. It also allows for missing steps and deviations. And also it's compact. Parameters grow linearly with the number of sub-activities. We tested our method on the breakfast actions dataset and the Inria instructional videos dataset. We are either competitive or we outperform these approaches, even though ours is fully unsupervised and these approaches are usually deeply supervised. Thank you very much.
Any questions while we have the next keynote speaker prepared?
So why do you think you outperform the supervised approaches?
So it's, I'm saying ours is completely unsupervised, but it's also kind of a bit supervised. So in our case, we assume that we are given the name of the complex activity. So we assume that we have the entire collection of videos which only belong to a complex activity, single complex activity. And then we don't use the we use the original features, so we provide the standard features, but then we try to create this clustering. And we kind of force similar sub-activities to be close to each other in this space. Then the temporal model is actually able to do some things on this new space, on this new representation. So, yeah, these are the reasons.